on a given face, the three uh, stress um, the three elements of the stress that act on that face, the three stress elements form a vector. And that vector is called the traction on the face. Um, okay, so it turns out that there's a relationship between the tractions and the stress tensor um, that that's really useful in calculations sometimes. Um, so the relationship between the stress tensor and traction vectors. Okay, so it turns out that if you right multiply the stress tensor with an outward facing unit normal for the face, the answer is the traction vector on that face. Okay, so let's see how this works. So let's say, for example, let's say your stress tensor is 5, 20, negative 2, 20, 0, 8, negative 2, 8, negative 10. Okay, that is all the symmetry that you need. It doesn't matter for this what the units are. Let's say it's megapascals. What is the traction vector on the x face? Okay, well, here's our cube, okay? And if you imagine the coordinate system origin being at the center, then an outward facing vector is in that direction, okay? This is the x, the y, and the z, okay? So what would a unit vector be in that direction? These, by the way, okay, these outward facing unit normal vectors, you can visualize those as like from the movie Alien. So these vectors are like the alien coming up, and this is whatever that guy's name was, right, coming out of his stomach. That's what I'm talking about, like it points from the inside out. Okay, so what are the components of that vector if it's a unit vector? Yep. So that outward facing unit normal is 1, 0, 0. And so the traction vector is, okay, so I got 5, 20, negative 2, 20, 0, 8, negative 2, 8, negative 10. And I'm multiplying that by 1, 0, 0. If you do this multiplication, you get a vector 5, 20, negative 2. We're still in megapascals. And that's the vector of force per area acting on that face. Okay? Well, that's not too amazing. I mean, it just isolated the element well, but it doesn't just work for, positive faces. First of all, it works for negative faces too. So what about on the negative y face? So we're going to take the same stress tensor, 5, 20, negative 2, 20, 0, 8, negative 2, 8, negative 10. And we're going to multiply that by the outward facing normal for the negative y face. So what's an outward facing, the negative y face is the one that we can't see underneath. What's an outward facing unit normal for that face? Yeah, 0, negative 1, 0. And so 0 multiplied by 0, negative 1, 0. And we get the vector. And yeah, so negative 20, 0, negative 8. Well, on the positive y face, we have the vector 20, 0, 8. Okay. So on the negative y face, we know from last class that on the negative y face, it has to be equal and opposite. So that gives you the traction on that face. Okay. So it works on all 6 of the faces. Okay. But it's actually still, that isn't too earth-shattering. But the next thing is what makes this really useful. So what if you multiplied by an outward facing normal at some odd angle? Okay, so for example, what if we used an outward facing normal of 0.7071, 0.7071, 0. So that's in the xy plane at 45 degrees between the positive x and the positive y. Well, that actually gives us something meaningful. So if you calculate this traction, So I'm going to use the same stress tensor, 5, 20, negative 2, 20, 0, 8, and then negative 2, 8, negative 10, and multiply it by this vector, well, that is, I could have done this with easier numbers, that's for sure, but, oh no, I can do it though. Watch this. That's 3.535 plus 14, 15.55, 56. Okay, I'll call it 56. And then what's the third one? Okay. So what does that mean? Well, that means that here's our coordinate system. I'm drawing it straight on, so the z-axis is coming right out towards us. Okay. And say that we had drawn our stress cube. So like when we defined the stress, let's say instead of defining it with a stress cube that had all the faces perpendicular to the coordinate axes, for some reason we had decided to define it at an angle like this, where one of these faces had the outward facing unit normal 0.7071, 0.7071, 0. Okay. Then if you think about this face, these values we got, 15.56, 14.14, 12.24 megapascals, would be the tractions acting on that face. Okay, so there's two ways that this is useful, only one of them in our class. So remember, like when I defined the stress tensor, I said, okay, define this cube. But right when we defined the cube, we oriented it to have a simple relationship with the coordinate axes, because why wouldn't we, You define it as simply as you can. And through that definition, we came up with this definition of the stress tensor. But what if in our definition we had decided to, say, okay, for this coordinate system, this is our stress cube, and then did the limiting procedure. Then that material that has this stress tensor the way we do define it would have this traction acting on that inclined surface. Okay. So it's not super clear what the use of that is, but it's kind of amazing that the stress tensor does that. You can see how that might be related in some way to representing a stress in a different coordinate system, right? So this is useful in two ways. The first one is in defining boundary conditions for mechanics problems. We won't use this But this is the kind of stuff that you do in continuum mechanics. So this is an important idea in continuum mechanics. So the basic way that works is if you have a material and the face over here has some loads on it, and you know the shape of that face, then because of the tractions that are actually acting on that face, there's actual loads that are creating actual tractions. You can use that relationship to put limits on what are possible stresses at the boundary. Okay, you really don't have to know any more than that. You probably don't even have to know that much for now. But the second thing is important to us. We are going to, so the principal stress is the stress tensor expressed in a coordinate system where there are no shear stresses. It's kind of an amazing fact that no matter what the state of stress is, there's some coordinate system where the only stresses are normal. Okay, there are none of those shear stresses. And this is important, practically speaking, for figuring out when stuff is going to break. And we'll talk more about that later. But this is a really important thing to be able to find. The derivation of the principal stress relies on finding those tractions on inclined faces. Okay, so this is the one that's going to matter for us in this class. And the last thing that you're going to need to be able to do with stresses is go back and forth. So there's this relationship between the stress cube and the stress tensor, and it's going to be helpful all the time to, when you see a stress tensor, at least imagine what that's saying about the loads on the stress cube.